Hi, everybody. Thanks so much for joining us today. This is Miran. I'm the head of marketing at Barbara. And welcome to our Talk to the Expert webinar series, where we invite our technology partners to share how their innovation are shaping the future of energy and industry. Today's session, Stabilizing the Grid with HEI, focuses on one of the biggest challenges in modern energy systems, maintaining voltage stability as more distributed energy resources connect to the grid. So we are delighted to have today Dr. Dimitris Lagos. He's a senior smart grid engineer at SMPnet, who holds a PhD in power systems optimization and control from the National Technical University of Athens. And also Enrique Ramírez, our senior solution architect at Barbara. Throughout the webinar, feel free to use the chat to ask questions. We will be sharing also useful links and resources there. And after the presentation, we will move into the Q&A session, and we will send you the presentation slides. And we also will appreciate if you could take a moment to complete our feedback survey at the very end of the event. So let's get started. Dr. Dimitris Lagos, the floor is yours. Thank you so much.
Thanks a lot, Miran, and thanks a lot to all the participants. I'm Dimitris Lagos. I am a senior smart grid engineer at SMPnet. As Miran said, my background is electrical engineering. I have a PhD in power systems control and optimization, and in SMPnet, I am leading the team of engineers that design and deploy the physics-based and AI-based solutions for power systems. A few words for our company too. Our company, SMPnet, is a software company based in UK. Our core product, Omega Suite, is a suite of advanced software designed for power system operators. And we have clients on UK, where we deploy our solutions to provide smart local power system operation and digitalized substation solutions. So having said that, I will share my screen and move to today's topic. Let me know if you can see my presentation. Great. So on today's webinar, we will focus on stabilizing the grid with Edge AI. And more specifically, we are going to talk about voltage control. Voltage control is a very critical service for power system operation. We have the very recent incident of the Spanish blackout, where, based on the reports that have come out, the voltage instability has been identified as the core reason that led to this cascaded disconnection of power sources that led to the blackout. On the right, I have some graphs of voltage measurements recorded in the system, and we see that there was some large voltage surges detected that the system couldn't absorb. And what we mean with couldn't absorb, we mean that the system was lacking enough voltage control capacity. That means that there wasn't enough sources available to perform the voltage control by providing reactive power support. Of course, this is not a new incident. In Greece, we had a similar incident also for a Greek non-interconnected island in Rhodes, where a blackout have occurred in 2016. The incident there was that the key synchronous generator that was mainly providing the reactive power support and voltage control was disconnected, leaving the rest of the resources having insufficient voltage control and reactive power support capabilities that led again to high voltage values, disconnection of distributed generation, and eventually blackout in the system. So, voltage control. Let's do a deep dive on how this is performed in power systems. Historically, in legacy power system, prior to the energy transition that we are experiencing over the last decade, voltage control was mainly a top-down function. That means that the main party responsible to perform the voltage control was the transmission system operator. So transmission systems provided the voltage support through on load tap changers at transformers and through bulk reactive power compensation, which means capacitor banks, reactors connected when we needed reactive power provision. On the distribution level, the DSO was at the tail of this hierarchy. So the DSO was mainly using similar approaches like capacitor banks, voltage regulators, and on-load tap changers in their transformers to perform voltage control. But this situation has drastically changed due to energy transition. At the distribution system level, we don't have only customers and demand at the moment, but also a lot of distributed generations, mainly renewable sources. That means that these sources can cause issues related to voltage control in the distribution network, but can also be utilized to provide the solution to these issues. And apart from providing solutions to the distribution system level, one thing that is important also to discuss here is that distribution systems can participate also in the transmission system voltage control. So how can they do that? I have a case here describing what is happening in the Swiss power system. So in that power system, there is a service for the TSO-DSO coordination regarding voltage control at the transmission level. So the Swiss grid, the TSO, every day sends a profile with 15-minute resolution of a voltage plan for every point of where a high voltage to medium voltage transformer is located, which are also the connection point of the DSOs. So the DSOs have to follow that voltage profile, and according to the measured voltage value, they have to either inject reactive power to the transmission system or absorb. So if we have an incident of overvoltage and the distribution system is absorbing reactive power, then it is compliant. It is on the green region that we see here because it helps the voltage control of the transmission system. If it is a overvoltage situation, then it should absorb reactive power to support the distribution system. If he does the opposite, for example, injecting reactive power when we have overvoltage, then it falls to non-compliant region. And through this service gives these incentives financially to the system operator to be on the compliant regions. So they are compensated for reactive power that is on the compliant region, and they have to pay penalties if they are in the non-compliant region. And through that way, they can support the transmission system. Of course, this requires an advanced control at the distribution level to ensure that based on the grid measurements that they have at the point of connection to transmission, they are able to control their resources in a coordinated manner to ensure that they provide service to the transmission system. So, of course, distribution system comes with its own challenges regarding voltage control. As we have DERs and loads to a distribution feeder, we can have various voltage incidents. For example, voltage rise if we have surplus of DER generation, or voltage drop if we have a surplus of demand. For example, if we have a lot of EVs charging at the network. And at the moment, the solutions to address these issues are mainly based on local or centralized rule-based approaches. That means that we have some static models and simplified rules with if-then-else logic that, according to these rules, they activate specific resources in the grid to resolve the issues. Of course, with this approach, there are several issues. For example, no one can be certain that all the different local controllers are being coordinated in a proper manner and they are not battling each other trying to solve the issue, and whether it is happening is the optimal in terms of efficiency for the distribution system. So the solution to that is to have an advanced centralized scheme. And to do that, this centralized scheme has to have a detailed network model, which means that it has a physics-based grid model with all the electrical characteristics of the network and the physical equations to model accurately the impact of the different resources. It has to be adaptive, so of course, this network model has to be updated with the latest status of breakers in the network to have the actual active topology and the latest measurements and forecasts to provide the optimal actions for the DRs. It has to integrate any local controls available. So if there is an OLTC there, it has to be its control integrated in the advanced solution. So in that way, the dispatch that will be calculated for the DRs will not battle the local controller and coordinate with him to provide the optimal solution to resolve the voltage issues. DQ axis prioritization, that means that we can use either active and reactive power to solve voltage issues. And through an advanced centralized scheme, we can have the respective costs for every solution. And in that way, it is prioritized properly with what should be used to resolve the issue. And of course, through an advanced centralized scheme, you can have also grid services like the TSO-DSO coordination scheme that we saw previously, as well as integration with local energy markets. So our software, Omega Suite, is designed to facilitate voltage optimization. So overall, our product has 3 different modules. So we have Aware. Aware is a dynamic grid monitoring tool that provides real-time insights and automated analytics to the system operator, as well as the forecast utilized by Optisys, which is the advanced dispatch and optimization tool used for wide area grid management. Optisys is the tool that we are going to see today in our webinar. And we also have Control, which is the dynamic real-time control for stable, efficient grid operations. So all of these products can be deployed either on cloud or on edge devices. So let's see here the solution overview of Optisys. So as we said, voltage management at the distribution level is suboptimal, and you can have uncoordinated controls between the centralized solution and local controllers. And Optisys comes to resolve this issue by operating as a wide area voltage optimization module for existing SCADA system and coordinating with existing local controllers. In that way, it can provide voltage management to the distribution grid and deliver voltage service to the TSO. So it can be multi-vendor and interoperable with system operators software. TSO-DSO can provide TSO-DSO voltage service. It can improve the grid stability by resolving over and under voltage issues and congestion incidents, reduce the energy losses in the system, improving the efficiency in operation, and increase the renewable energy penetration. So at the moment, we have a use case on a European DSO where the Optisys is utilized for a wide area voltage optimization, and is integrated with the SCADA system. This integration goes with the ICCP protocol, where Optisys gets the latest measurements from the SCADA system, perform its calculations, and then send back the dispatch command to the DSO SCADA that then uses another protocol, in that case DMP3, to control the different DRs in the network. So Optisys is managing the wide area voltage optimization through a real-time digital twin, a model of the network with a physics-based model with all the electrical characteristic of the network, that it is updated with the latest status of switches to have the active topology on every Optisys run, and then perform an adaptive optimization of voltage using this physics-based model. And through that way, it can provide improved grid stability and efficiency, reduced operational cost, and high renewable energy penetration. So the deployment options for voltage control schemes that we discuss in this presentation can be either local. As we said, we can have local controllers that measure a point in the network and make decisions for the DERs. Distributed controllers that can coordinate the operation of multiple DERs. A centralized solution that can talk to every DER and make decision. And a hybrid solution that can combine both centralized and edge devices. So for local or distributed designs, the issue is that you might not get an optimal solution, and you might end up having the local controllers coordinating poorly with one another. In a central solution, you can have an optimal coordination of the DRs, but you end up with a single failure point, the centralized grid management software. So the hybrid approach can combine the benefit of both options. It can have the optimal operation of a centralized grid software and also have the robustness of operation using also local edge devices that can operate in case of a central software failure. So having said that, I can move now to a demo of our solution. Hope you see my screen. By deploying our solution in an edge device, this is an actual edge device that is operating on a demo network that we have in our lab. The user can see initially the Omega logger, so they can see the different processes running, the control, forecasts, and Optisys. And then it has two different user interfaces that the user, the system operator, can interact. One of them is the user interface designed to have the network topology and the user preferences. So by clicking network data, the user can open an Excel file that can see, for example, here we see the transformer data. No, actually we see the storage DR, whether it can be, its active power can be controlled, the upper and lower limits on state of charge, charging costs. Same with DR like photovoltaic and wind turbines, where the user can set whether the unit can, the Optisys can control the active power of the unit or reactive power. Other data included are the electrical characteristics of the network, so the physical model. We see here the lines, the connectivity between the buses, the electrical characteristic of the lines, also the buses and the voltage limits that will be taken into account by Optisys to compute the dispatch of the resources. And finally, there are characteristics about the transformers, if there is a tap changer, and the electrical data of the transformer. By modifying here, for example, there might be a maintenance on a line. The user can set here false in service and let Optisys know to avoid taking this line into account in its calculations. So by making the change and by pressing set network data, the network, the physical network that is being considered by Optisys is updated. Of course, this is only for the static data. Optisys constantly updates the network based on the latest status of the switches. So if a switch disables a line, this is also taken into account in the digital twin model and being considered by Optisys. So apart from network data, we have the user data. In that file, the user can set the different options in control. So for example, by setting control value to their reactive power to false, only active power can be used for voltage control. Whether Optisys can control the OLTC tap change. This is also something that can be introduced in this sheet. Strategy here have to do with if the operation of the network is isolated, that means that no interface with the transmission system is considered. In market participation, strategy means that specific generators should follow market generation profiles by Optisys. And finally, the terms of the objective function used by optimal power flow engine of Optisys. So here, the user can select the different factors that should be taken into account by Optisys in calculating the optimal dispatch. So, for example, the curtailment of renewables, the curtailment of load. We have a storage in this model, so the utilization of storage, active power losses, tap changes in the transformer, and so on. So apart from this user interface, we have also an active dashboard. You see here the active dashboard of Optisys, where the user can see the actual data calculated from Optisys, as well as the latest measurements. So the first two tabs, user settings and network and their data, they are linked to other dashboards that present, for example, the network data that have been given by the user. So the user can go in here and check if everything has been processed correctly, and check what is the network at the moment that being considered by Optisys. The same goes for the user preferences too. So let's go back. So Optisys, the rest of the tabs, has, for example, presents the forecast to the user. So we will see that the dispatch commands are also calculated. So the users here can see based on what forecast these commands have been computed. So we see the wind turbines forecast for the next 24 hours, photovoltaic forecast for the next 24 hours, and load forecast for the next 24 hours, which is followed by DER and loads. So for the rest of the graphs that we will see, on the left side is what happened in the last 24 hours. And on the right side is what is forecasted to occur in the next 24 hours. So we see the total generation of renewables, solar and wind in the system load. We see the wind turbine active power generation, curtailment. We see that Optisys resolve issues, either congestion or voltage issues in the network, by controlling active power of DERs in this scenario or reactive power. So we see here that there are several cases that it has issued curtailment for the wind turbines to resolve an issue in the network. And also we see here that it has issued also reactive power commands to support the voltage in the system. The same goes for the photovoltaics. No curtailment for the photovoltaics, but there is a reactive power dispatch, and it's also reactive power dispatch that is being scheduled for the next 24 hours. I should also add here that Optisys is adaptive, so it is executed every 5 or 15 minutes, depends on the user preferences. So these profiles are being updated every 15 or 5 minutes or 30 minutes based on the latest forecast and the latest measurements from the grid that give also the active topology of the grid. So even if there is a 24-hour horizon in the graphs that we see on the right, these are being constantly updated. So they get always the latest status of the system into account. Also here we see energy storage system, the active power and state of charge evolution throughout the day, and the generator active power. There is also a thermal generator in the model. And apart from that, Optisys calculates also the voltage profile for the next 24 hours. So we see, for example, here that there are some voltage limitation limit in this system is 1.12. That's why in this time period we saw that there is reactive power dispatch and active power curtailment to resolve the voltage issues. Let's continue. If there was a voltage violation in these graphs, we will see in which bus and for how many minutes the limits have been exceeded. Now we see that with the Optisys dispatch, we do not have any violation in the voltage. In addition, there is different graphs that give to the user what is happening on the line. So we have active power, reactive power, apparent power on the lines, as well as the current on the lines. The most important graph, of course, is the loading that gives the percent line loading. We see that the same period here that we have voltage issues, we have also a congestion incident. That's why we don't see only utilization of reactive power to resolve the voltage, but also the curtailment of active power, because only by using reactive power, the voltage issue would have been mitigated, but the overload issue would not have been resolved. And that's the actual benefit of having a centralized approach with a digital twin of the network, because you can have the impact of the different strategies, curtailing active and using reactive power to the whole network. And while a local controller would only see a local voltage issue, dispatch reactive power to resolve it, and then it wouldn't know that in another line this reactive power dispatch would cause a congestion. So apart from the lines, of course, we have graphs on the transformers. Same situation here with the lines, active, reactive power, currents, and the most crucial graph, of course, the loading, that there is a congestion issue that is being resolved by Optisys dispatch. And finally, the user can see the power losses computed in the network through the digital twin, as well as the headroom of the transformer in the past 24 hours and the next 24 hours. So with that, I conclude the demo that I would like to present to you, and I will give the floor to Enrique to show also their end and how Optisys can be easily deployed through the Barbara platform.
Thank you, Dimitris. Thank you. Yes, and that is exactly the point we want to show about this way of using Barbara to deploy Optisys application in different edge nodes. Okay, when it comes to deploy something in the edge node, at the end, Barbara is a really helpful platform. We are an edge orchestration platform, and that means that we can help our customer to deploy application and AI models easily in the edge node. And that is exactly what we're going to do today. Okay, I will start sharing my screen, and I will show you the main interface of Barbara. You can see it here, okay? And well, what we have here is a list of different edge nodes that we have available for an organization, okay? We can see where are they located, and we can see we have different industrial PCs or virtual machine deployed on any customer facilities, and we can select any of these machines and we can start working with them. Okay, I will just start declaring that the Barbara is a hardware agnostic tool. That means that we can run an edge node using different kind of machines and different kind of vendor. We can see here the full list of the equipment that are compatible with Barbara, okay? And the way of provisioning one new device in the platform is really easy. We just need to select the machine we want to use, okay? We have from physical devices and also the possibility to use a virtual machine to deploy the application. For example, if we want to use some specific equipment, we select the equipment we want to use. In that case, we download the OS, the Barbara OS, what we call Barbara Core. This is an OS developed by us internally. It is based on Linux, And the good point about having our own OS is that we designed it to be cyber secure. Okay, so from the very first minute, the equipment and the OS are compatible with the AIT 62443 specification for cybersecurity in industrial environment. And this is very important because make all the solution secure about against attacks. Okay, so this is the way of provisioning one new device. Very easy. We just need to install the OS in the equipment, and after that process has been finished, we will see one new equipment here, and we can start working with them. Okay, so imagine we want to deploy the Optisys application in a edge node we have in some substation and somewhere where we need to start working with Optisys. Okay, we can enter in this device. We have here all the information about the hardware itself. Okay, in this node information area, we have here the network card where we can configure everything related to the communication of that equipment. We have here a VPN that will be very important because it will allow me to access this device remotely in a secure way. Okay, and I will use also this IP of this equipment to access the Optisys application. Okay, well, I can see here the telemetry of the equipment. We have several information, but let's move to this part where I can deploy the application in the edge node, and here is we will deploy the Optisys application. The good thing about the Optisys application is that you can see here our marketplace. Okay, we have plenty of application here, and Optisys is one of them. Okay, so we have included in our marketplace. It is available here to be add to our library, and here we can see all the information about the application. We have all the information about how to configure this application and install them remotely. Okay, we can see here all the information. So the way to deploy the application remotely in an edge node is really, really simple. We just need to add a new application. Here we will select Optisys. Okay, we can select different version in case there are several. Okay, so we will obviously select the last one, and here we will have the wizard that help me to configure everything necessary as detailed in this technical node we can see here. Okay, so I just need to follow this wizard to configure all the parameters needed by the application, and finally I send the application to my edge node. I will see that our new card will appear indicating that the Optisys application is deployed on the edge node. I can see the version, the status. I can stop and start the service remotely, and I can configure everything again if necessary. Okay, so here I can change any configuration whenever I want. Increasing a lot the speed of working with the Optisys. Here at the end, we can see also the logs of the application on real time. So now the question is, how can I access this in this dashboard that Dimitris showed before? It is really easy. I just need to use the IP that I have here for this edge node. So I will copy this IP, and this way I can use this IP and the port where the dashboard are available, and this way I can enter in the dashboard that we could see before with Dimitris. I think the application is starting, so yes, we can see here all that information that Dimitris showed before, and the same for the UI that Dimitris also showed before. So this way, once the application has been deployed, we can enter in this panel and start working with that. So imagine the amount of time we can save deploying the application this way. And also not only deploying, but also updating, reconfiguring. So all the process to work with the application remotely is really, really optimized this way. Okay, so I think that is a good overview, okay, of the way of working together. So I don't know if we have any question in the QA section, Miriam.
Well, we have a couple of them. One is, this is for Dimitris. From your perspective, what are the most critical gaps in DSOs and PCO coordination today that technologies like Optisys or edge control platforms aim to address? That's one of the questions that we want to launch from Barbara.
Okay, thank you, Miren. I would say that the main challenge is that software platforms that aim to facilitate TSO coordination are interoperability and fast deployment. So that's why in SMPnet we have designed the Omega suite to be both protocol agnostic and grid agnostic. That means it can support various protocols, so they can interface with different software either used by DSO or TSO, and also to be grid agnostic because DSO TSO coordination could differ. It could have different local grid characteristic in one substation and completely different to another. So our solution and any solution that wants to facilitate DSO TSO coordination should be interoperable through being protocol agnostic and grid agnostic. And apart from that, it has to be designed in a way that will be fast deployed to any substation or any system. So this is where the collaboration with SMPnet and Barbara can come into play, as Enrique presented, and help deploying really fast our solution to edge devices in different environments and locations.
Okay, following that, just this is for you, Enrique. How will you, we're talking about high availability. How does Barbara provide high availability? That would be one of the questions.
Okay, thank you, Miren. That is a very good question. Yes, that is also a possibility we have in Barbara. Let me share again my screen very quickly so I can show it to you. We have the possibility using Barbara of deploying application not on top of a single edge node, but on top of a cluster. Okay, so we have here the cluster functionality where we can create clusters composed by several edge nodes. It doesn't matter if they are the same hardware or not. Okay, we can use different hardware depending on the possibilities. But here, for example, we have a cluster composed by 3 different edge nodes that are working with synchrony. Okay, they're working together. So now what we can do is deploy an application exactly in the same way we show with a single edge node, but now using a cluster. So now, if any of the edge nodes that are involved in this cluster have any problem, for example, any hardware problem, any power supply problem, or whatever, the service will not be interrupted because the application and the data related to that application will be moved to the other available edge node. So this way, we can guarantee that the services that have been deployed in the edge node, for example, the Optisys application, will be running 100% of the time without any kind of interruptions.
Okay, thank you so much. Dimitris, this is for you also. As energy system become increasingly digital and data-centric, what are the main characteristics of a voltage control solution?
Okay. Through the energy transition that is happening now, the system operators are being proceeding with a digitalization of their infrastructure. So they have being installed equipment to collect a huge amount of data from the network. So eventually, AI and machine learning techniques will be part and are already part of software that have to do with grid management. So having that in mind, such solution should, I think, cover 3 key main aspects. One is that they should be deployed fast, which I covered in the previous answer. So they should be protocol agnostic, grid agnostic, and being in platforms that can be deployed fast. The second pillar is that they have to be secure. So the software solution should be designed according to international standards like ISO 27001 in order to ensure that they are cyber secure and resilient. And in SMPnet, this is something that we follow and we are compliant to that ISO. And finally, this is a more strategic, let's say, pillar is to provide AI models that are interpretable and should be combined with physics-based models. if we consider that power systems are a critical infrastructure. So if you go to a system operator and you tell him, okay, I train this black box with your data, take it to your system and it will control your resources, they will never accept it. They will never accept a black box that they cannot predict how it will behave. So it is important that this solution should be based also on physics-based models and are interpretable. And there are very few teams in the world that doing this at the moment. And at SMPnet, we have some of the top engineers in that field in our team, and we are proud of that.
And this is also for you, because I mean, you are our guest, so the questions are all directed to you. How do we overcome the barriers and create the conditions for innovation in grid management?
Yeah, I would say again, being cyber secure and be resilient is the main factor, because we are talking about a very critical infrastructure, the power systems. Of course, as I said, fast deployment, so grid agnostic, protocol agnostic solutions. And finally, real actual demonstration. So in order to overcome these barriers, these innovative solutions have to be implemented in parts of network, so their actual value, and then proceed building the trust of the system operators to a higher scale in their networks to provide the benefits that they can give.
Okay, well, we do not have more questions. I mean, I've been trying to, see whether we or attendees if have any questions, but I don't see any. So, well, thank you so much.
Mira, sorry,
Yes?
I think we have one question.
Oh, really? Oh, yes.
Yes.
Oh, thank you. Oh, thank you so much.
I don't know
Thank
if you can see it.
Yes, I can see it. Oh, thank
Okay.
you. This is like,
I think this is for me too.
Yes, yes.
This is from Rafael. Let me read it for you guys. In the case studies mentioned, voltage control was managed through a combination of local OLTC actions and centralized optimization. So how do you see this balance evolving in future DSO systems?
Yeah.
Thank you, Rafael.
Yeah, that's a really good question. So have to take in mind that system operators already have equipment in their system for voltage control that they spent millions installing and they've been using for many years. So no solution can go to these networks and ask the DSO to replace them or take voltage control by itself. So the vision and where the power system control is going is that you have to provide a solution that should take into account these local controls, because they will be there and they will be operating, and your solution have to do that. And this is something that we take into account in Optisys, where we include in the optimal power flow engine all the local control dynamics, so we would know the impact of our dispatch to the local control. And in that way, we can have an optimized operation with all the control sources in the grid and not battling with them and causing coordination issues.
Well, thank you very much. Any more questions? Now I'm looking at the right panel just to see whether any of our attendees have any other questions. I think we do not. So, well, we're reaching the time. Dimitris, thank you so much for joining us today. Enrique, likewise. For all you attended, please be aware that we will be running new Talk to the Expert series. We will invite new technology partners. And thank you so much for attending. And please do, if you don't mind, fill in the survey that is going to come afterwards after this webinar. So thank you so much all for coming, and thank you again, Dimitris and Enrique. Take
Thanks
care.
a lot.
Bye.
Thank you very much.
Bye-bye.
Bye-bye.
Bye-bye.